Hey guys, I'm Charlie. I'm the team lead. This is Tyler, our structures lead. Marta, she's on structures. Michael, he's on structures. This is Iber, our avionics lead. Erika, she's on avionics. And Kenneth, he's on avionics. We're an all-freshman team from the Illinois Space Society, the SETS chapter of the University of Illinois Urbana-Champaign, helped by CIA mentors Mark Joseph and Jonathan Sivier. Our team with 24 motivated, driven freshmen is what makes us unique. We have the largest Midwest high-power rocketry team in ISS history. There are 23 of my closest friends, and I can guarantee you anybody on the team would say the same. Pictured is our intramural soccer and frisbee team, which not only created team bonding, but improved the team dynamic at our meetings.
Since the rocket has to fly at supersonic speed as efficiently as possible, we decided to construct the rocket with a minimum diameter of 54 millimeters. Because of the challenge, most of the following design decisions were based off of reducing mass and making sure the features of the rocket are compatible with the minimum diameter rocket. This is MIND. It will fly once on the required I-218 motor and again on the Roni J430 motor. It's made out of Bluetooth and has 3 sections: the upper airframe, which holds the avionics section, the middle airframe, which holds a coverage payload, and lower airframe, which holds fins and the motor. It has a predicted maximum Mach number of 1.14 and a stability off the rail of 1.39 for the first flight and 1.17 for the second.
To find the most efficient motor for supersonic flight, a score was calculated for all Roni Aerotech I and J class motors. The choice was between the Roni J430 and the Roni J1055. Both motors allow the rocket to achieve a supersonic speed. However, the Roni J430 was chosen due to its much lower peak thrust outweighing the effect of a slightly higher apogee and a slightly higher impulse. The data in the table was obtained through open rocket simulations.
So this rocket has a P2 for data gathering, so we utilized CFD to figure out the best placement for it. We decided to place it at the tip of the nose cone instead of the side of the airframe in order to avoid an oblique shock at supersonic speed and to obtain more accurate pressure measurements. Along the open rocket, we use FinSim, where we can alter the design of the fin in accordance to the divergence Mach number, as it is crucial that the divergence Mach number exceeds the predicted maximum velocity. If it doesn't, the fins will break at the predicted maximum velocity. So we have 3 triangular fins with a sweep angle of 66 degrees and a ripcord of 6 inches. The recovery system is composed of a 30-inch main parachute and a 9-inch drop parachute attached to the rocket with a 15-foot Chatha shockboard. Due to space constraints, both parachutes are tightly packed in a parachute protector and are found in the same compartment. At apogee, an electronically triggered ejection charge will separate the rocket between the upper and the middle airframe. There is also a backup charge, which is slightly larger than the main one in case the backup fails. The descent speed for the drop parachute is about 100 feet per second, and at 700 feet off the ground, an electronic shock release will deploy the main parachute along the rocket to achieve a descent speed of 20 feet per second until touchdown.
The rocket utilizes the Strandwater CF as the primary altimeter and a altimeter telemetron as the backup, which is configured to trigger a 2-second delay after apogee. The avionics team elected to use lithium polymer batteries over alternatives because they have a higher energy density and are cost effective. We also utilize screw switches over the more traditional rotary switches because they are smaller, lighter, and more robust.
So we decided to use a printed circuit board as the avionics sun system for our commercial and non-commercial data logging sensor suite. We decided to do this to reduce mass as well as to optimize the minimal amount of space dedicated to avionics. The flight computer, our Raspberry Pi, collects data from all of the sensors, stores it on board, and then relays it to the ground via a live telemetry system. These sensors, including iometers, pressure sensors, and a lead sensor, are daisy-chained using I2C communications. The memory and telemetry module are wired in SPI configuration to ensure a faster and more reliable connection with the Raspberry Pi. We constructed a set of rails which lines the inside of the avionics bay. These rails are meant to securely fasten the PCB in place during flight and to minimize movement. They also allow us easy access to the board before and in between flights. The PCB is sandwiched between the upper bulkhead and a 3D printed piece placed in the nose cone to reduce vertical movement during flight.
Harley competition bonus points require a camera that can see both the ground descent as well as
parachute deployment, and flames of the rocket upon launch. To achieve this, we used a 3D printed piece with mirrors on it so that the Raspberry Pi camera on board can see both the nose cone and the bottom of the rocket. To achieve the telemetry bonus point challenge, we utilized a RFM 96 LoRa radio module to communicate non-commercial flight data back to the ground station where it can be viewed.
The airframe was originally cut using a handsaw, which was sanded down later to eliminate discrepancy. The motor retainer was then epoxied to the lower airframe using JB weld. And since the motor retainer has a larger diameter than the airframe diameter, we put a small piece of Bluetooth underneath the rail guides such that they would not interfere with the motor retainer. Forged eyebolts and bulkheads were placed into 2 couplers using rock epoxy, and the couplers were placed into the airframe using a number of 1/4-inch fillets. Originally, the rock design had the lower eyebolts placed a foot into the airframe, which impaired our ability to tie a shock cord to the eyebolt. As a result, we split the lower airframe into 2 separate subsections connected by couplers and plastic rivets in order to make the eyebolts more accessible.
We incorporated into our design a pitot tube sticking out the tip of the nose cone in order to add another measurement of velocity to further verify accelerometer data. When we were assembling the nose cone, however, we realized that the original pitot piece was actually too wide to fit in the narrow nose cone. So to account for this, we replaced it with a custom 3D printed piece so that the static ports of the pitot tube can stick out the tip of the nose cone.
So our fins are made out of a 1/8-inch plywood core, which we laminated ourselves with carbon fiber. Once the carbon fiber cured, we sanded the fins down and we tailored the exposed edges. They were first attached to the lower airframe into slots that we cut into the airframe, and they were epoxy bent to it. However, the fins themselves do not go through the entire tube as they would interfere with the motor since our rocket's main diameter. So we employed a technique called tip-to-tip to further secure them to the airframe. Essentially, cutouts of carbon fiber were layered and laminated on both the fins and the airframe to ensure a stronger attachment and to also decrease water.
Test flight. We lost our rocket. GPS went out on the pad, and the tracker likely went out when the rocket hit the ground because it probably came down ballistic. We spent over 6 hours searching for the rocket in Tabitha. Good part was we got to use our pre-flight procedures and see which parts need to be changed before the competition. A problem we faced with launch were switch holes around the same side as the rail guide, so we had to reach around the rail guide to turn on our avionics bit. Needless to say, the rocket did not meet our expectations at the flight.
Since no telemetry data was recovered from the flight, another software was needed to predict flight performance. Randeo 2 was chosen due to its high level of accuracy with an average error of only 3.68% due to sophisticated modeling techniques. The data in the open rocket was corroborated with the data in Randeo 2 with very little difference in top speed and peak altitude.
After a post-test flight assessment, the team came up with likely causes of failure in the rocket from non-ballistic. The most likely cause that we found was that the lithium polymer batteries disconnected from the circuit board. In order to combat this, we decided to use 3D printed battery retainers, which would keep them more secure. The second likely cause is that the altimeters came loose due to vibrations in flight, and since we have used electrolyte all the mounting hardware on the Avionics bit. The third likely cause of failure is that the terminal wires disconnected from the terminals. And for this, we decided to use threaded wires instead of solid wires because we believe that will give us a better connection. The less likely cause of failure could be that the rails suffered a structural failure, and for this, we widened the rails, which allowed us to use a substantial fillet. The least likely, but also still possible cause of failure is that the circuit board suffered the structural failure itself, and for this, we thickened the PCB by 20%.
After losing the rocket, the team could not have possibly been more optimistic and ready to get back to work. The second time around, the team had a clear idea of the challenges that came in constructing the rocket and found a quicker way around them. For example, we cut Bluetooth with a miter saw instead of a handsaw for a cleaner cut. The rails were more secure onto the Bluetooth, and the switch holes were placed on the proper side with respect to the rail guides, so we could turn the avionics bay easier on the blade. Thank you so much for your time, and we'd like to open it up to any questions.
How are you planning on getting your PO to build up this work?
So we have a backup PO tube in case that the PO tube does in fact get clogged. That was unclear. I'm so sorry. There's a backup nose cone with the PO tube already installed. So all you have to do is just replace the nose cone and you have the same functionality.
And then your SD card on here is contained. So you want to use it to your SD card.
So the SD card is actually a backup memory storage system. We have a onboard SPI memory chip that works through SPI, which is hard soldered onto the PCB. So we're a lot more relying on that one. But we'll still be taking the SD card on there.
So you test it without the SD card and make sure that the software doesn't crash.
Yeah.
And you test it with your SD card out and do an operation to make sure the software doesn't crash.
You said you didn't get telemetry data from the flight. Did you at least have a link before you launched? So it was running when you launched. You just lost it while it was flying. Okay, thank you.